Welcome everybody to our second CUDAN seminar, which took a week of break due to NetSci conference, which we all attended, and now we're up for more leisurely talk. And so let me just introduce the speaker, who is Thilo. We met about, oh my God, 13 years ago, I think, at EECS in Dresden, which was a conference on complex systems. And so Thilo has a PhD in physics, if I remember well. He had a group called Beyond, awesome acronym, about biological dynamic networks at a time when the word dynamic and networks were sort of not exactly in the same room all the time. And now you are, in the meantime, you have been to Bristol, sort of down the road from Massive Attack and Banksy, and doing equally cool research. And then you changed to UC Davis, and less than a year later you changed to Oldenburg, because that seems to be more awesome, at the Helmholtz Institute for Marine Biology, where you are studying ecology using physics. But in your track record along the way, Thilo has a constant stream of cultural stuff coming out that trickles and simmers right beside, but is super interesting, about biodiversity in Egypt via artworks, about the stability of forms of governments in phase space, and I think we met also, actually, upon Thilo's invitation. You did also in 2007, I think. No, forgot the year. We did something on networks and music, which brought together a very wild variety of people, from the founder of Ableton Live to neuroscientists that do Indian classical music, from acousticians to art historians. And so there is a shared interest in A, multidisciplinary research, and B, culture. And I thought there is a lot of stuff that you contribute to the multidisciplinary community, which I wanted to very early also sort of share, A, with the group, and also with the wider audience that is sort of plugging in from outside. So let me introduce my group a little bit. So on the screen, you see Mila Oiva, Mark Arnett, Anna Yammer, and Xenia Mukina, and Andres Karjus. They're all fellows, postdoc, or PhD students. We also have a guest, Tonja Wick. And then locally, we have Jan, Mark, Tilman, Vijune, and Antonina, who are also PhD students and postdocs. They're all PhD students, one postdoc. And so the idea is we spend a lot of different kind of things we do, but there's a common thread, which is cultural data analytics. And yes, we're very curious about what you are presenting to us today. I have to give a spoiler. We talked for the last 6 or 7 weeks, every week for 2 hours, because we have some ideas about what we can do in cultural analysis. And you're gonna give a little glimpse of one of the opportunities, which is very much cutting edge. So please take it away, and the stage is yours.
Hi, yeah, Max, thank you very much for the nice introduction. You kind of what I also wanted to start with, but actually I have to admit, if you all my awesome title, right? It's not my title, actually. Max gave it to me, and I think it's slightly preposterous that I should be talking about cultural analysis, because, you know, after all, I'm kind of at an institute that is mainly known for running icebreakers, and somehow that seems a long leap, yeah. But all my life, I've been doing things like math and ecology and physics and network science and a bit of data analysis, and I was thinking, what I'm really interested in is also culture, and I think, not always, but sometimes, these kinds of methods that you learn when you're a physicist or a mathematician or a computer scientist, they can help us understand culture. So, and to motivate a slight bit, right? Why would you be interested in ecology? Well, I would say because ecology is the discipline that has struggled with complex systems for over 200 years, yeah. Because ecologists were always aware that ecology is basically a big network of interacting species or interacting individuals. And ecologists have really struggled for 2 centuries to find good strategies to make kind of sense of these systems. And particularly, they have a long tradition of data analysis. They have a strong focus on how different things emerge and how different things can classify and why things compete against each other and why they can nevertheless coexist with each other. And if that somehow starts to sound cultural, that's slightly intended, right? So that's ecology. And physics on the other hand, hasn't dealt so much with complexity. It's much younger. The physicist's interest in complexity is only 70 or so years old. But there's another thing that physics does exceptionally well, and that is mathematical modeling. So what physicists are always good at is figuring out the big picture by ignoring the small details. And basically in physics, it's done with mathematics, right? And physicists have been very good at coming up with these strategy, how to describe systems mathematically and understand them. So does cultural analysis need mathematical modeling and data analysis? And I have to say that depends very much on what you want to achieve. If you want to understand things at a microscopic level, talking about individual works of culture or individual people, then probably you know you don't need these things. If you think about the bigger picture and you want to understand the bigger picture, not on the scale of the individuals, but on the scale of more like themes and streams and topic and so on, styles, yeah, then methods from math and physics and ecology and computer science can help a lot, because we have some methods that allow us to coarse grain and see the bigger level. And particularly today, I will talk a lot about data analysis. But before I talk about data analysis, I also want to talk about the kind of other modern superpowers that we find in this toolkit. And this is mathematical modeling. And so I won't talk about too much paper level stuff, but I'm feeling nowadays data science gets a lot of attention, but mathematical modeling is actually in the midterm even the more important thing and the more powerful thing. So, and I want to use this opportunity to share some things that I have learned about mathematical modeling and that I feel are the biggest misconceptions people outside physics and mathematics have about modeling. So one way, so you can say, why would we need a model? Yeah, why would you model a system? Well, people always think models are tools for prediction. And that is true partly, right? That's not completely wrong. We use models for prediction, right? The weather forecast is made with models. But even the weather forecast is only made with models for about 10 years. Yeah. Before that, the weather forecast was not based on models. And that is because you need an awful lot of information to make predictive models. Models can be also used for something different, and that is as tools for understanding. That's where the true value lies. And to understand this, think of a model as an experiment where you have complete control over the experiment, over every aspect of it. I will show an example in a moment that makes it much more clear, I think. So I want to give you a brief overview of how a physicist would think about modeling. So, and I want to start with a very simple, very old-fashioned, very dusty example of network science, right? And I guess you have all seen this, but maybe you don't have seen the point I want to make with this. So suppose I make a model, and in my model I say, well, I want to describe a network of people So the nodes in my network, they are people, humans. The links in the network are personal contacts, acquaintances, friends, whatever you want to call them. And I will assume, and that's the assumption that I put into my model, everybody has 100 friends. And I also assume that the network is organized such that there are no short cycles in the network. And of course, at this point, you notice I'm starting with a wrong assumption, right? Not everybody has 100 friends. And also, of course, in the real social network, there are lots of cycles, right? Two of your friends are very likely to be friends with each other. That's the famous clustering coefficient. So there's a lot of cycles. So nevertheless, I want to work on this completely wrong model because that's a model I can actually analyze easily. If you look at what happens, I can count the number of people at distance 0 from me. Yeah. So that's just one, that's just myself. I can count the number of people at distance 1 from me, 1 link away. That is just my 100 friends. So the answer is 100 exactly. And I can count the people at distance 2 from me. And let's say every one of my 100 friends has 100 additional friends. So then I get about 100 times 100. And because I have said there's no small cycles in the network, these need to be 10,000 different people. So 2 steps from me, I find 10,000 people. And then, of course, I can easily generalize it. If I go d steps away, I will find 100 to the power d people. Why do I do this? I do this because I now can, for instance, compute how many steps I need to go till I found everybody. And you realize, right, because we are doing a very rough model, let's say there are 10 billion people in the world. So what can I do? I can say, to what exponent do I need to raise 100 to give me 10 billion? And mathematically, you can write this as a log, and you find the log of with base 100 of 10 billion is 5. So you get an idea that probably I could reach everybody in my social network in 5 steps. So these are, counting myself, the famous 6 degrees of separation. So why do I show this simple example, right? My point is, here I've been making a very artificial, relatively wrong model. But even this very simple, very artificial wrong model allowed me to understand one thing. And the one thing is, why is this diameter so small? Yeah, it's because the number of people I reach grows exponentially. And even though my model was hugely oversimplified, and based on wrong assumptions, this insight is actually the right insight. And now if I make my model more realistic, this insight will stay. So let me say some things. These are kind of about 4 or 5 things I learned the hard way about modeling. And my first thing I learned is, if you model, you want to model phenomena, not systems. Yeah, and in speaking, you always speak like you were modeling systems. Yeah, somebody would say, oh, I model birds. Yeah, no, but people always model phenomenon. Yeah, the model I just presented, that was not a model of the social network. Yeah, because if I had thought of this as a model of a social network, this would have led me on the wrong track. It would lead me to make the wrong assumptions. No, I wanted a model here that describes distances and diameters in social networks. So a phenomenon, the small word phenomenon. So nobody's ever modeled a bird. Yeah, people have modeled bird flight, people have modeled decision-making in birds. Some people model bird metabolism or bird neurology or bird reproduction, yeah? But we model always a phenomenon, never the system. The second thing I learned about modeling is you want to be unrealistic. Realism is not a good property for models. It's not something you want actually to have. You want your model to be unrealistic. In fact, you want your model to be as simple as possible. And if that means sacrificing realism, yes, go for it. Why is that? Well, basically, we do models to understand the world. But if I make a model realistic, that means I make it as complex as a word, and then I cannot understand it. if I go for a hugely oversimplified model, yeah, what happens? I can mathematically analyze it. And maybe you noticed it on my previous slide, right? There was no simulation of my model involved. I looked at my model and I was able to understand the complete behavior for all possible distances that I can put in. We could easily generalize to all possible number of friends, right? You don't have to study these things separately. You can solve it mathematically in one go. So a simple model, you can analyze very quickly and very completely. And maybe if you oversimplify things, you will just understand that your model is bad, that it's wrong. But by knowing how your model is wrong, it will give you an idea how to improve it. And it's much better to have a model that's too simple and that you can understand and understand how it goes wrong than a model that's too complicated, so you can't even make a start on the analysis. So what else can I say? Now, how do we make a model simple? Well, we make it simple with wrong assumptions. And recently I had a reviewer write back to me about a quite actually detailed, fairly realistic model that I've spotted this assumption which I don't actually totally buy into, and I'm not sure how something can ever be said based on a model that is wrong. Okay, now I have to say that's a wrong attitude. So there will never be a right model. We are not in the capital T truth business, right? This is not the religious department. We want to make a model that is as simple as possible and just good enough that we can understand the tiny details that we didn't know before. So when I call this, so the parable of the bottle, so that's a little story I like to tell to make this a little bit more intuitive. So the problem with modeling is for modeling, you don't have to be clever. You have to be brave, because you need confidence in your own model, yeah? And if you ever talk to a physicist, you know, physicists always they have this overconfident attitude, yeah? So sure, you studied 30 years of biology, but I can answer your question just with a pencil and a piece of paper, yeah? So because you need this attitude in physics, because you need this confidence to trust your own models long enough to actually analyze them. So I want to tell you this little parable of the bottle. I have a bottle here. This is a bottle. It contains very nice whiskey, and it says there is a liter of it. Now, if you look at this bottle, it doesn't look so big, actually. How can you be sure there's a liter? Well, you can never be sure, right? That's the thing about religion. But can we maybe increase our confidence that it actually contains a liter? Well, I can try to compute the volume of this bottle. So how do you compute the volume of this bottle? This has a very complicated shape. I'm not sure I can do this. So what I can do is approximate the shape by a cylinder. Now I've approximated it, yeah. And now I can compute the volume of the cylinder very easily. I measure the radius, I measure the height, and then I can easily compute the cylinder. I have a mathematical model for the volume of the bottle that I can actually solve mathematically, and I'm done with it very quickly. So, and this isn't perfect, right? This bottle has a different shape than the cylinder I put it in. So I was basing this on wrong assumptions, but probably most people here agree, right, that we are happy to accept these kind of assumptions because we slightly somehow feel in control of that. We know there's going to be an error, but we feel this error is not very big, yeah? So actually, when I made my little model about the social network and I said, oh, we're not allowing any short cycles, you've probably felt that was very wrong. That was very unrealistic. But actually, the estimate that I get with that for the diameter of networks is much better than the diameter I get by approximating this pretty cylindrical bottle by a cylinder. So if you look at my slide, I can apply this to the data of Facebook in 2011. And John Ogander did actually a big study of Facebook where he used the whole Facebook topology, meaning every user, every link, to compute the diameter of Facebook. And it turns out that the true diameter of Facebook was 4.6, and that is a big, large supercomputing task. On the other hand, my little pen and paper estimate would say it's 3.8. It's not an exact result, but it shows you somehow doing a little model gives me kind of good idea. So, and by making wrong assumptions, we get models that we can study and we can see them fail. And if we can see them fail, well, we can always fix them later, make them more realistic. And in this case, I can put the cycles into my little estimate. It makes the math slightly harder, but it doesn't make it impossible. And then this value, if I put cycles of length 3 in, so friends of friends, so the 2 of my friends are likely to be friends. If I put this in, this estimate changes from 3.8 to 3.9. So actually doing this is not a big correction to my model. Anyway, what do we do if models don't fail? Yeah. Well, we have to break them ourselves before somebody else does. So if you have analyzed the model, the next thing to do is always to make it wrong, to find the limit in which it makes totally wrong predictions. Yeah, because by studying the way in which your model fails, you actually know what's wrong with it, right? You know, you can back analyze which assumptions cause this failure. I can again consult my bottle here and say, okay, my biggest error comes from this bit here, it's the neck being much, much thinner than the body. So the cylinder approximation is good till about here. And then I have this bit. So maybe next thing, we don't approximate it by one cylinder, we approximate it by a big cylinder and a small cylinder on top. Yeah. So the wrong model gives me always ideas for a better model. Yeah. You maybe have heard this. A classical physicist insult to say about somebody else's ideas is not even wrong, right? Because being wrong is not an insult. Being wrong is what we do in order to get better. Yeah, every model is wrong in some way because no model captures the complete world by design. So every model is wrong. That's good. We break them, and in the way they fail, they tell us more what we need to learn. So a wrong model is great because it shows somehow your intuition was wrong. You need to improve your intuition, and the model shows you how. If you have weird ideas that cannot be studied mathematically, your model is not even wrong because it cannot even be falsified. So it cannot even lead you to better ideas. So what has this got to do with cultural analysis? I think in all cultural disciplines, yeah, modeling is presently underutilized. Modeling was underutilized in biology about 10, 15 years ago, and now it's huge. And nowadays, there's as much knowledge gain, I think, in biology from modeling as there is from data analysis or from primary observations. So, and some things modelers have been studying on networks, and these are just random examples from my own experience, is, for instance, epidemic spreading, right? Oh, well, that's very current, right, with the virus now and so on. But models of epidemic spreading, they model how things are copied from person to person. And so they can also describe the propagation of ideas, of concepts, of knowledge, etc. We have been studying models of opinion formation, how people make up their minds, how ideas are exchanged, yeah, how ideas compete, how ideas evolve, yeah, if they come into conflict, yeah, on a network. So this is this whole bunch of opinion formation models and models of consensus. Do you think this could have maybe some use in understanding culture? And finally, in ecology, we talk a bit of coexistence of different species, yeah? So why do different things coexist? How do they get along? Why is that even possible? And this has some influence on culture. It's very closely related to actually models of culture. For instance, models of linguistic evolution, like there's this naming game and all kind of variants of it. So almost the problem is in culture, I see too many things that could be done with mathematical modeling. Okay, so I want to give you one very small but very concrete idea to illustrate why we need maybe models to understand cultural phenomena. And I know people on your side are very interested in movies. So a while ago, I noticed that if you come back to what I talked about, the small world phenomenon, right? Of course, the movie phenomenon connected to that is the Bacon number and the distances from Kevin Bacon. And if you study this more closely, you see that Kevin Bacon is not the best center of the movie network. Nowadays, it changes very quickly who the best center is, but it's always a relatively famous actor. And so far, it's always been a man. And now you can make your list of the best centers of the movie actor network. So the people who are closest to every other actor. And if you make this list, you see that the top best centers involve very few women. And that's very surprising. So the first woman in the list of best centers is only 54. So only the 54th best center is a woman. The first 53 best centers of the movie network are men. So the first best centers, that's a woman, is Susan Sarandon on 54. And then among the first 100, you only find 5 women. Yeah, so 5%. That's pretty strong disparity. And it doesn't get even better if you look at the first 200 or so. So what's going on here? Why is that? There's also another funny thing going on there. Maybe people have noticed it, maybe not. If you look at these names, Susan Sarandon is the only one that's not British. Why? Yeah. Anyway, is this a cultural difference? Is there something? So, but the first question: why are there so few women in the best centers of the movie actor network? Are there just fewer female actors? Do they have shorter careers? Have they got a lower rate of appearance in movies? Are they more consistent in their collaborations so that they are close to the same people in all their movies and don't do so many different things? Maybe they are more faithful to the genre, yeah? And the problem is, if I try to approach this by data analysis, I can't really answer this question, yeah? Because data analysis only takes account of what is there, yeah? In order to ask about causalities, what causes this, I need to talk about models. So what could I do? Well, I could make artificial worlds. I could make artificial actors of networks. Say, if I make my artificial networks of actors, I have control over the proportion of women in the network. And if say, oh, if there is a disparity, maybe in the number of female roles in movies or in the number of women in the system, or if there's a difference in careers in my artificial network, I can ask which of these factors would lead to a disparity that is so strong as the one that I observe in the real system. And by doing this, a modeling study can reveal causality, yeah. Okay, so I've talked a lot about modeling, and I talk relatively abstractly. I now want to get much more concrete, right? And I want to talk about real data and real data analysis, and a phenomenon that's not totally cultural analysis, but it's related. So a while ago, I lived in the very nice, beautiful city of Bristol, next door to Banksy and Massive Attack and all kinds of other cool people. And this map here basically shows Bristol, but all this red stuff shows something else. This red stuff are the so-called census output areas. So that is actually shows you what kind of data you can get on Bristol. The UK Census is the census. It's basically a thing that's done with questionnaires every 10 years. The last census was 2011. Every household has to answer a questionnaire by law. So we have a lot of very detailed data. We don't get the detailed data for privacy reasons, but we get aggregated data. And what they do is after you have all the census data, they aggregate households that are similar and close in space so that we get areas in which 40 to 100 households are aggregated. And these are these census output areas. And that means that the countryside, these areas are huge, but in the city center, they are very, very small scale. So the data that we have from the 2011 census in the UK, in the Bristol area alone, that is 3,850 of these output areas. And for every output area, the census reports 1,499 different statistics. So that is an awful lot of data. And it's not an awful lot of data. If you think about this as a data table, your table would have about 4,000 rows, which is smallish, I would say, but it has 1,500 columns, 1,500 features for every little area, which is pretty huge. There's actually not many methods that can deal with this sort of data. In fact, the people who can generate this data, they say, oh, nobody can work with 1,500 statistics. So this government office that does this data gathering and data analysis, the Office of National Statistics, they say, oh, in our analysis, we only take account 90 of these 1,500 things that we measure. So there are some methods which you can still use to analyze these data sets. And one method I want to present here today is diffusion maps. That's not by me, that was published by Ron Koisman and his lab in Yale some years ago. This is the original paper. And this hasn't been used too much, actually. Also, the method is pretty awesome. So, why is that such a problem? Just want to mention, once you work in a data space where you have 1,500 dimensions, basically, that's a huge space. It has 2 to the 1,499 corners, which Google says is infinity. Yeah. And for practical reasons, it is infinity. The number of corners of the space in which your data points are located. That is more corners than the universe's atoms. Yeah. So this space is not filled with data points, yeah, not by a long shot. The data actually in this space of things we measure, so this data in the space of parameters, that fills a very low dimensional subspace. You can think there's only some manifolds, some membranes that lie in the space that are filled with data points. So to analyze this data properly, we have to detect these membranes and we have to find new variables that describe where we are on the membrane. So actually, if that was very abstract, I will make it more concrete in a minute. I want to illustrate one other thing first. And that is, if we take different areas of the city, they can be very, very different in these 1,500 different statistics. And the problem with comparing very different points is that the points you compare, you can't even quantify how different they are if they're very different. Okay, let me make this very concrete. So if this was very abstract, let me make an example. Look at these three objects. Yeah. You can compare these objects and you pretty well know how to compare. You probably even get an idea which of the three are more similar to each other than the third one. And if not, you can probably bring these three things into a meaningful order, yeah? So, well, it's not a big secret, right? They're all trucks, they're all blue. And they differ very strongly in size. So you would say, if you compare them, you could say, oh, that's the smallest one, it's like 2 tons. And then we kind of have our 8.5 ton, and then we have our 40-ton truck. It's very easy. Well, what about changes? What about these three objects? How do you compare them? You can think about them and you kind of get ideas, right? But which two are closer to each other than the other one. Or, so funnily, if I ask this question, statistical evidence says that half the audience always has an idea which ones are too closer. The problem is all combinations you could argue occur. So you could argue, well, two are kind of still vehicles, and I've kind of primed this interpretation by my previous slide, right? But you could also say, oh, two of them are toys. Or you could say, if you're more interested in culture, say, oh, one or two of these things are stereotypical American things. Yeah. Well, anyway, my only point is, if you're comparing very different things, it's very hard to quantify the differences. So if this argument looked too silly to you, let me make it more concrete. So this phenomenon I'm talking about is we have a big space of many, many different things that are measured, but for illustration, I just put two axes here. So our data points, or little areas in my case, they have values in these things. But I say most of the space is bound to be empty, and the data is bound to occupy only some manifolds, in this case a line, in this space. And if you have such a situation, right, you don't need these two variables independently. The only way in which these points differs, how far are they along this axis? So to enable a meaningful analysis, you should work with this variable, the right variable. So this is very easy if it's just a straight line, right? You could find this variable by things like PCA or so. But that only works if things are linear, and in the fields where I work, things are never linear. So what if your data looks like this? You can see that, again, it's on this manifold, on this spiral here, yeah? But how do I actually find this from the data? And the problem is, if you do your PCA, it gives you trash, rubbish. And this is because PCA uses long distance comparisons. And here, by the way, I can illustrate my point that I made. Very similar things are easy to compare. I can quantify the distance between these 2 points here. But different things are not very easy to compare. I would think that these 2 points are actually close together if I just measure the distance here. And this point here is farther apart from this than this one is. But if you realize that all this data lies on the spiral, right, in order to go from this point to this point, I probably have to go all the way around here. So this distance is actually very far, and this distance is by comparison smaller. Now, what can I do? I can basically mark on this chart all the comparisons that I still trust because they are short enough together. And I get a network. I get a network of points where the links mean these are things that I can compare meaningfully. And now you see this network almost already traces the shapes that we want to get out of our data. I can now see that this maybe is an extreme point, and these are extreme points here, and then there's a continuum between them. How do I actually extract this? Well, I propose the following. If you're a computer scientist, you could compute the shortest path, say, and you could measure then which are the points that are farthest apart from each other and so on and so on. That you can do that, but that's very noisy. Another thing you could do is, if you're a physicist, you could start a random walker here and let this random walker walk randomly on this network. That's a process that's very much like diffusion. And you can measure your expected time since your random walker reaches a certain node. And that is your new variable, the time, the expected time till your walker gets to a certain node. Or if you are a musically inclined person like Max is, right, you could think, hey, we can maybe build this as a physical object and then strike it with a hammer and it will vibrate and make a sound. And all the parts that vibrate in phase, they are somehow close together. You would think that this bit, these nodes here, they all vibrate together. These nodes vibrate together. Yeah. So maybe this is our new variable. Who do you vibrate with? Yeah, we give all the things that vibrate together the same values. Or if we have this physical object, we could heat it at one end, and we could measure the time that the heat needs to get to a certain node. And this would define a new variable. Yeah, if you heat it here, this would be the last place where the heat arrives. So the beautiful thing is now that all these processes, diffusion, heat conduction, mechanical vibrations, they are basically described by the same mathematical object. And I don't need to build it. I don't need to simulate it. I don't need to analyze it. I can just solve the equations. Yeah. And the equations tell you, you have to compute the eigenvectors of a certain matrix, a Laplacian matrix, and that tells you the time evolution of your heat or your walkers or your sound for all time. So, and this way you can find the right variables. So this is a diffusion map procedure. I don't want to actually talk about this in much detail, but I want to make the point. Once you understood the math, the data analysis is actually 5 steps or so. Actually, the Python program that we use to get the results that I show you in a minute is just 10 lines long. People keep asking me if I have a package for that. No, I don't have a package because one should understand the math a little bit. And once you understand the math, you can implement it in like 2 minutes. So like any good magic, right? Good magic, it's hard to understand, right? Some precise words make a magical spell. It's not hard to say it when you know what the words are. Diffusion map is like this. It's hard to come up with a mathematical procedure. Once you know the mathematical procedure, it's very, very easy and very quick to carry out. Let's get back to Bristol. So I do this. I take all this data, I build this network, I compute this matrix, or Laplacian matrix, and then I compute the eigenvectors. And then these eigenvectors, they give new variables to each of my little areas. And these new variables that I identified in this way, I've color-coded them here. So this is Bristol again. You see the streets, yeah, there's a river here, the River Avon. And now when I saw this picture, I said, oh, it seems my method is working because the data set doesn't know about space, it doesn't know where the areas are, but it seems it has picked up some signal here. There is this big blue blob that appears in the center of the city. So this is not just population density or something, right? Because these are also densely populated areas here. So what is this? Well, and we have some blue noise around here, but I said, okay, this is big blue center. Since I lived there, I just said, maybe let me just walk there and go there. And I didn't have to walk very far because that is just outside my door. That is actually here is the office I was working in. And the center of the blue, that is the University of Bristol. Okay, good. So I said, okay, that's interesting. Now, if I looked at the other blue dots here, these blue dots here, at first I thought they were noise. And then it occurred to me, wait, no, I know these places, yeah? Because the biggest blue dot, that's the University of Bristol. But if you zoom out a bit, you get this picture. Here again, University of Bristol. But these other places, they have a meaning, yeah? And the next big blue dot you find here, that is Bath Spa University. This is actually Bath City Center, where we have lots of things from the University of Bath. Here's the main campus of the University of Bath. This is the University of West of England at Frenchay. This is a technology center of the University of West of England and University of Bristol together. That is the second campus of the University of West of England. These are the halls of residence of the University of Bristol. So, what is this signal we are picking up here? That is where students live, yeah? So what my analysis tells me is my algorithm has picked up a way in which people are similar and has found, oh yeah, the students, they're all pretty similar. And that gives me a first notion of similarity for the city. I can also now look at my second eigenvector. So that's my you know what I said with these three objects, right? Things can be different, similar in different ways. So this, where do students live? In Bristol, that's the most important way areas of the city are similar. The second most important way in which areas of the city are similar is this. So this looks a lot more patchy. So what do the blue areas mean here? Well, again, I walked to them and one blue spot looks like this. So this is social housing. That's the so-called council estate. So that's social housing that the cities used to build for poor people. Nowadays, it's all sold off. It's in private ownership. But poor people still live there. So I went to the city council and I asked them whether they have a list of all the council estates, and they have them. So, and it fortunately has the geo coordinates. And now on this map, this is the background is my eigenvector. And now here I put these dots, which is the location of former council estates. And you see there's a pretty good agreement between them. So there's one dot, which is not on blue, that's here. That is a very, very small council estate. It's not these big buildings. They are actually very small bungalows, and there's only 20 of them. So they are actually not very expensive. And not poor, apparently, anymore. But other places have become expensive, but they have still the signal of poverty. So you also see there's some blue places which don't have a dot. They are still council estates, but I don't have the data because here that is the edge of Bristol and they technically belong to the county of North Somerset, so I don't have data there. Okay, so we can find poverty in Bristol, right? Actually, we can find it on a very small scale. Let me zoom into this tiny little area. This is how it looks zoomed in. And here I've walked every street and I marked our buildings that once belonged to the council or in which the council is still renting a lot of flats. So the yellow buildings, these are the actually outlines of the buildings. There's two green ones, which is a hospital and a city-owned home for the elderly, where basically low-income old people can live that wouldn't have a place to live otherwise. And so we almost get a building level accuracy with this kind of analysis. So, and basically here you see there's a lot of area around the buildings that's also blue. That is because things are clustered in these finite areas. And much of this area that's blue here is a public swimming pool where nobody lives and a park where nobody lives. Yeah, get the picture. So then we thought, hey, that was UK. Can we also do this for the US? So we did Los Angeles. And so that is the first eigenvector for Los Angeles. These are two different zooms. And it might be hard to see if you have a small screen, but there's just some very, very small red dots in this first eigenvector, the first most important way in which things are similar. These red dots, they correspond to UC Santa Barbara, Cal State, UCLA, California Polytechnic, Pepperdine University, and so on. So this analysis for the US, with the US Census now, picks out all the universities in the Los Angeles area in this case. We can use it the second way in which things can be similar. What's our second eigenvalue? I wonder, will it be poor people again? Will it be social deprivation? It turns out not. Here, that's the second eigenvector. This first thing here, that's the most red in this case, it's called FCI Terminal Island. FCI stands for Federal Corrections Institution. That's a federal prison. We have another federal prison here. We have California State Prison. Here down the list, we have an immigration prison. So the second eigenvector that perfectly picks out my prisons in the area. And there's an interesting story here. This California almost had its coronavirus outbreak under control. And they had an outbreak in this prison called Chino. And it turned out it was kind of a twice capacity. So they tried to transfer prisoners quickly out of this prison. And of course, they only transferred prisoners who had tested negative for coronavirus. Unfortunately, some of these prisoners had the tests 2 months before. So, and with this, California very, very effectively spread coronavirus from this prison to all prisons in the state. And if you look at my list of prisons here, one of this is called Francisquito fire camps. Because in California, the firefighters who fight the forest fires, they are all prison inmates, or a good fraction of them is prison inmates. And they all get coronavirus now. Eh? All crises are now one crisis. Anyway, I want to talk about social deprivation here. So let's go on. What's the next most important thing, and which things are similar in the US? Well, turns out it's military bases. So again, my eigenvector perfectly picks out the military bases here on the coast. So that was the first three. What about the fourth? Well, it turns out the fourth is social deprivation, we think. That's an interpretation. But this is not a black and white thing. This is not like the military base. If we're saying something is a military base or it isn't, you get a much more gradual signal. So you get some areas which are deep blue, and these are super deprived areas, really. These are kind of textbook examples of social deprivation in California. And you get also some areas which are very bright red. And most of the really, really bright red areas, well, there's Beverly Hills, which is kind of red, but there's also the brightest reds in country clubs and in gated communities, and particularly in retirement communities. Yeah. So this is different from the UK. In the UK, the main divide was between the middle class and the very poor, while we here detect a much stronger divide between the middle class and the rich. Also in the UK, we didn't have a strong racial signal. In the US, we have actually a very strong racial signal. And to make these maps, we stripped actually the racial information out of the census, because black and poor is so similar that we didn't know whether we were detecting poor or we were detecting black. Actually, the analysis I showed, we didn't only do Los Angeles, that is actually a zoom into an analysis where we used the whole country. So you can see patterns of all scales. On this big scale here, you see a lot of native reservations, which stand out as particularly poor areas. There's also some other, the so-called southern poverty along the Mississippi River and eastern Texas, California Central Valley. These are kind of poor areas that we find also in this analysis. We can also zoom in. For instance, we can zoom into Florida. This is Florida. And you see here, Florida is a super heterogeneous state. It's much more heterogeneous than all other states. You can zoom in a really small area here. This is an area of Palm Beach. I could have done Miami. But here you see deep red. That's an area of very expensive, very nice houses. Just north, where it's not quite so nice, but still nice, there's a place here you might have heard of that's called Mar-a-Lago. And you see just next to this is pretty deprived, very poor neighborhoods. And then we have basically a trailer park here that's it's super deprived. So, brief note, we can also do this for ecology. Yeah, we took all bacteria and we took the actual genomes of all bacteria and we reconstruct the metabolism from the genomes, and then we diffusion map the metabolism. And what you come up is just different strategies that bacteria use to survive. So this is basically the tree of life of all bacteria. And you see what I've color coded here on this inner bar again. This is one of the eigenvectors. And that eigenvector basically tells you who does photosynthesis. Yeah. So the algorithm has figured out that doing photosynthesis is just a big decision for bacteria. That the most important measure of similarity in this case is, do you do photosynthesis or not? That's the most important decision that you have to make if you're some bacteria. So, and there's other life strategy choices. Maybe I don't explain them so much. I just wanted to mention those because this paper has just come out. And what I mean with just, I mean like 2 hours ago. Okay, so I'm over time and at the end of my talk. And so I think, okay, data analysis is fun. I think we know that already. But I basically want to argue that this method, diffusion maps, has big potential actually for analyzing culture. Because we could run this method directly over, say, products of cultures like pictures or music or so. And ideally, we first figure out some properties that describe them. But if we can map a work of culture to a vector of maybe some 100 or some 1,000 descriptors that I generate maybe, say, with a neural network, then I can use this coarse-graining ability of diffusion maps to maybe identify styles and different types of artworks coming up or something like this. And so we get the ability to ask the question, what are the different styles? What are characteristic examples? When do the styles emerge? Maybe we can do the same for the artists themselves. And so are there different types of people in this? You know? In the long run, this might be combined actually with mathematical modeling to maybe understand how have humans come up with their names for artistic styles, for artistic genres, and so on. So this could be combined with a study of naming games and so on. Yeah? Why is this a genre and this thing is more like a subgenre, but not a genre in its own right? All these things, I think, can be studied now. They are in the scope of what we can do with data analysis and mathematical modeling. So sorry that I can't present really much results in this realm yet, but I think that is a very interesting area for potential future collaborations. And I think, and I want just to share the thought, I think cultural analysis, art history is very important because for humanity, art might be just this area where we can study how humans discuss their perception of reality, how they define different terms. How do I agree on what a cubist is or what an impressionist is? And if I can understand these mechanisms of opinion formation and evolution of ideas, say, in humans, I might also be able to understand why our democracy and opinion formation processes in politics go off the rails. And it might be much easier to study this with an art first than to try to straight away apply it to politics. So thank you very much for this perhaps slightly unusual, sometimes very abstract and sometimes maybe too concrete talk. But I hope it has given you some ideas for a nice discussion. Thank you.
Thank you very much. So thank you. That was great. Good mixture of being specific and broad and theoretic. So yeah, the purpose of this whole seminar series is to have discussions, and there's two options. One is to speak up one after the other. The other one is like put a question in the chat. In order to know how we are doing the sequence, I think it makes sense to just like at least just put one character in the chat if you like, so we can actually see who lines up, and then just go one after the other, whoever comes first, if that makes sense. So who has the first question? Maro's already like unmuting himself.
Yeah, I think even you touch, I mean, my PhD research is about latent space navigation. And you actually touched the point with the diffusion maps that actually can be studying, basically going there and kind of reduction of the dimensions. And I was actually thinking this weekend on collaborating with Daniel, that is another researcher that he has like analyzed movies, and I was like thinking how I could like act different things on the latent space and then navigate, and then you show this of the diffusion maps, and it makes a lot of sense to kind of explore this direction of like kind of finding points and relations and so on from different like like latent spaces of different content actually.
That would be.
Can you develop on this, or can you? It's not a.
Yeah. So this is a very nice nice idea, and I can maybe add one little story here. We have actually used this to navigate actual space.
Okay, then you can point me to some literature. I mean, I will be more than happy to if you.
Yeah, sure. I mean, I can probably talk by email or even have another detailed Skype about how one would implement that, right? But let me say, since you phrased it in terms of navigation, right? So there is a problem that's called a wireless location matching problem, and that is you have say a factory that has smart light bulbs, so that the light is only on in places where it needs to be on because the worker's just there, and so you're in the future you envision that these light bulbs are like Wi-Fi enabled devices that have a small Wi-Fi unit in the light bulb. And you know exactly the places where light bulbs are installed, but you don't know which device it is which was placed. So you have to somehow figure out who's where. Yeah. And our idea was to, so what the measure is the strength of the signal they get from others. And people have tried to do this matching, and there are some solutions for that actually that are commercially implemented, but they are very computationally intensive. So you can't do them on the light bulb itself. So our idea was we do this matching, but we do this matching in a new space, that is this diffusion space. And that works very, very well. And yeah, that's another paper that I didn't mention. Sorry, just somehow when I hear navigation, I have to tell the story. But yeah, that's a very nice idea. And I would be very happy to be in touch and think about this.
Okay, thank you.
Thank you very much. Who else? Should I ask a question? Maybe you can talk a little bit about this. So we had this discussion coming from the problem with these multidimensional spaces, like networks in general. If you draw a node link diagram, are often more multidimensional than, you know, they don't lend themselves to actually see a lot. And then if you do this like in general, where you embed paintings, say, into multidimensional space with machine learning, or any other multidimensional data, like the census with 1,500 columns, it's not really easy to draw this nicely out. And so the methods that you refer to principal component analysis, which is around since 70 years now, I guess. Which is
that's been around a while,
right? Sorry? Even longer?
That has been around a while, yeah.
Yeah. And then, so there is in between, there is the things that are hip right now, like TSNE and UMAP and stuff like that. So this may be things that people in the room have heard or have not heard, but, you know, we should all look up if you haven't heard it. But could you explain a little bit, like, why diffusion maps? Why not TSNE? Why not UMAP?
Okay, so there is very different ideas about so it's funny, all these methods that you mentioned, they look like the same thing, but they are very different things when you come to actually high dimensional spaces. So I would say there is different classes of methods. First, there's linear methods. PCA is a linear method. It is nice, it works well if the thing you're searching for is linear. It pretty much falls apart if this is not. In the American paper, we have done the same with PCA, and you see there's some big patterns survive, but you don't get this like track by track accuracy. Yeah. So let's forget about PCA. Let's talk about the others. I would say there's two traditions. One tradition is the people who naturally think in high dimensional spaces. And they are typically mathematicians. They have very beautiful mathematical ideas. So they are these very solidly mathematically grounded methods. Things like basically actually putting a spline through the data with conjugate gradient methods, or multidimensional scaling, or the diffusion map, yeah, or Laplacian eigenmaps, or UMAP. Yeah, these are strongly theoretically grounded methods that are inherently designed for high dimensional data. Then there's a different category, and these are methods that come from visualization. The basic idea behind them originally was to put points in a space for visualization, to visualize networks. And these methods are, for instance, they're all neighborhood embeddings, yeah? I think the biggest one is No2Vec, yeah? From computer science. Then there is various visualization methods, and TSNE is one of them. The NE and TSNE is neighborhood embedding, yeah? So, and they are based on a low-dimensional intuition. And they are good for putting things in 2 or 3 dimensional spaces. They're not so good for putting things in a 10 or 100 dimensional space like we do. And TSNE actually, and this has been shown mathematically, TSNE actually becomes a clustering algorithm if you're on high dimensions. So it's not even extracting these manifolds anymore properly. TSNE makes all data look like cluster data. There's a paper by Moon that actually shows it very nice. So anyway, so I'm not so much interested in the methods that are ad hoc. You can do that and it kind of works. I like the methods that are grounded firmly in theory. So you have a pretty solid mathematical understanding why they work, and you don't have to fiddle with parameters because you understand what the parameters do. Basically, the diffusion map and the way I use it only has one parameter, and that is what you consider a neighbor, what you consider close enough. And this parameter is how many neighbors do you keep. I keep usually the top 10 best neighbors, and this number 10, that's the only parameter in my method that I have to fiddle with to make it work. So there's not much cherry picking involved. So now you can ask, okay, what's the difference between Laplacian eigenmaps, multidimensional scaling, diffusion map, and UMAP? Multidimensional scaling is beautiful, but it needs a lot of data. I don't usually have so much data. The other 3 methods are all based on Laplacian eigenvectors. And UMAP is the one you use if you like simplicial complexes. Diffusion map is the one you use if you don't like simplicial complexes so much and you like simple math. And Laplacian eigenmaps is the one that you use if you like even simpler math. And they produce basically almost the same results. It's almost one thing that goes by 3 different names, I would say. Yeah? So I like the diffusion map. For me, that's a kind of good trade-off between being very mathematically grounded, strong in physical principles, but still very applicable to the data I have, working fine in terms of results.
Nice. Anybody else? Yes, Mila, please speak up. Should I unmute you or yes?
Yeah, I'll do you hear me? I just unmuted myself. Thank you, first of all, so much for this talk. I really enjoyed it. I'm a cultural historian, so it was good because it was simple, so I understood it also. I'm very interested in kind of like what you would call like diffusion of knowledge or in history or kind of like in the science in the, well, how would I say that? Well, in history research, when we study circulation of knowledge, we kind of like nowadays look at it not only as a diffusion, but there is also important factor of the feedback, and that kind of like based on this understanding, the kind of like information moves, but also there is kind of like feedback, and it kind of like information moves based on this kind of like discussion or movement back and forth. So I'm kind of like curious, are there certain kinds of ways to model this kind of like movement back and forth, and at the same time like kind of like diffusion of kind of like, or changing of understanding maybe?
That's very cool, because that's exactly the kind of discussion we really need to have, yeah? Because that's interesting for me, because it gives me now something, new to think of, what I was not aware of. So your subject knowledge can be integrated into models. So, okay, so what has been modeled, of course, a lot is epidemics. And in a certain sense, right, my most naive model of diffusion of knowledge is epidemic spreading, yeah? And I wouldn't even call this a diffusion process, actually, because in classical diffusion, you have particles that move, and if they move, they are gone from where they left. But of course, in diffusion of knowledge, you infect others with your knowledge, right? It doesn't mean you lose it because you shared it. Yeah? So now you say I shouldn't be modeling this just as an infection process, but maybe there is different things you can be infected by. So there's almost competing epidemics, but there's also interactions between these epidemics. So this is something that similar things exist in ecology, right? If species spread across the networks, they kind of infect habitat patches where they can live, but they also interact. And sometimes a species can come in if another is already established, but sometimes also there's a competition situation where species can't come in because another species is infected. So these are things that are presently modeled. So the question is, what is the nature of your feedback? Yeah, can I describe it in such a way, or is it something that needs more or different mechanisms? So if you understand, if you can identify exactly what the mechanisms are you want to describe, I'm pretty confident we can get them into models of knowledge diffusion. And my goal would be to see whether our understanding of these models leads us to identify phenomena that can then be confirmed in data.
So can we, do I understand you right? And that obviously the diffusion that we were talking about casually is epidemic spreading of knowledge from person to person, for example, so stuff that moves, while the diffusion and diffusion maps is more like a study of stuff spread out, in essence. So it's not the kind of...
the diffusion map is a bad name, yeah, but the diffusion map takes its name from this idea of diffusion, which is really walkers moving around on a network,
okay, yeah.
Which you never see and never simulate, but somehow this is let's say it's a historical term, yeah?
Yeah, okay.
But mathematically, that is what is actually described. So for me, there are two fundamental basic processes you can happen on a network. One is diffusion. Things get transmitted, but they leave the node they come from. And the other is infection. Things get transmitted, but a copy is made of them so that they can stay in the node where they come from. Yeah, physical money, yeah, coins and so diffuse across the population, right? While ideas are shared, they affect people. So the diffusion map, you could say, draws on these ideas, but it's not modeling this in this sense. It is just a tool, it's just a mathematical tool to understand the shape of data sets.
Nice. So would it make sense to, I don't know, we had this in a conversation between the two of us. So there's one of the issues that is going on in the science in general is that people always look for causation, right? It's like one of the problems that all these psychology papers have and evolutionary psychology papers have, where they do like some linear regression on some diffuse data sets of points in order to get to causation, which you probably can't. And the cautious humanist and the cautious physicist would probably not actually always go for causation, but first we need to see what's actually moving, how is it moving in general, what like very old school physicists called kinematics, which is a word that is almost like extinct, right? So
I wouldn't say, not among physicists, I would say.
Okay. So,
I mean,
so what you,
to fill this in, right, the classical physicist narrative comes with another understanding from mechanics. The first generation was Tycho Brahe, who measured the positions of all the stars there on his private island in Denmark, and just wrote long and long tables that almost looked like social science. We have all these observations and observations and observations. Then came Kepler, and that is what the diffusion map does nowadays. Kepler found that all these observations fit on a lower dimensional space. The time of rotation of a planet is linked to its orbital diameter and so on. Kepler found all these laws, the kinematics of the thing. And the third step was Newton, the dynamics. And in that step, we have the causality. Newton says, yeah, the planets and the stars, they move in this way because of gravitational force. So there's a claim to causality. So it's important to do the kinematics. And I would say the word is almost extinct because we have a new word for it. And this word is data science. Yeah. Data science is a new kinematics. Okay. And we also have a discipline that extracts causality. That's called mathematical modeling.
Okay. Well, okay. Yeah.
And with modeling, you can find causality. That is why we need modeling. That's why we have modeling, because you can detect causality.
Interesting. Okay. Somebody else? No questions? Okay. Daniel, yes, please unmute.
Yes. Am I unmuted now? Yes.
Daniel joins us from Manila.
I do, yes. Hi. Great.
Hi to Manila.
Thank you for a great talk. It was fantastic, very thought-provoking. I have a couple of questions. One has to do with going back to the earlier part of your talk when you talk about the common idea that not all models are wrong, but some models are useful, no? Which is, I think, the common aphorism. And I think I really like this idea of using models to explore as ways to explore things, and you breaking them as ways of understanding, how they're wrong and so on. But it also seems to me that there is a need in order for us to infer or to reach somehow causality. There is the need to map inputs to outputs in terms of these models. How would you say this happens with kind of modern deep learning, machine learning techniques in which this mapping is not very obvious or not very easy to make? No, I really like your thought of simple mathematics. I think called machine parsimony, or this idea of simple ways of modeling, precisely because then you can just work your way backwards from them. Yeah. But what happens when you have like a huge set of ways that are just matrices of numbers that have very little meaning, and it's really hard to map them to their inputs, so to speak. No, does that not then make causality really difficult?
Yes. That was a short answer. Want a longer answer? Actually, I had this ongoing discussion with one of my Bristol colleagues who went around and gave these talks saying, we have Moore's law and computers are getting faster so much that you don't need to do modeling anymore because we will do just everything with data analysis. And because every 2 years, every 18 months, the speed of computers is doubling, data analysis will just outpace any modeling, any theory you can do. And that would mean we don't understand anymore because neural networks are not good tools to understand things. And my answer to that would be, well, the point is, even if you believe that Moore's law continues, that computers will continue to get twice as fast every 18 months, which is very doubtful. Yeah? But even if you believe this is only exponential growth. If you take a very simple mathematical problem and I add one more node and one more link, most problems get combinatorial, more complex. So I would say computers become faster at the moment, maybe still exponentially fast, but the world gets more complex. factorially fast. So I think to keep up, we will need to do more than machine learning. Yeah, our understanding has to grow. And these two things will go hand in hand. So neural networks and so on, they're not tools for understanding. They're not meant to do this. They are pattern detectors. Yeah, they are. They do a good job. They do an impressive job at detecting patterns. They are also good predictors. They're tools for predicting that. They are very powerful, but they're not tools for understanding. Yeah, and I think if we as humans want to understand something, there's no way around the simple mathematical model until we have human-like intelligence in a computer who can do it for us.
I've got a similar related question, which is what we put into, like nowadays you can put anything in neural networks and something comes out, right? The key thing is like understanding is one thing if you look at like data with many dimensions, which we just did, right? Mm-hmm. But there's obviously different data types. There's images, there's videos, there's text, there is classifications, and so on. Much like you can basically imagine the world as a table with infinite amount of columns for every item, whatever your items are. You can imagine like folding this in and making one network out of it with different link types, which people also do, right? So you have sort of a source and a target and anything in between. And there it's not so obvious as with the kind of matrix with lots of columns, what actually are you doing when you diffusion map it, in essence, right? So the key thing is not like a kind of dimensionality reduction, but you have these three columns, source, link, target. And then the question is almost, in the first place, how many dimensions do you have? Like how many dimensions does my network have, for example?
Yeah, but that is actually easier, I would say, yeah? I can diffusion maps a table, but what I do to diffusion maps a table is I turn it into a network.
Yeah.
If I have a network straight away, I don't need to turn it into a table first. I can use this network straight away.
And so basically you turn that list into the matrix it is, and then basically feed that to the, okay, yeah, I got it.
Yeah, you turn your network straight away into the matrix. You don't need to have a table in between.
Yeah.
And connected to this, I think AI has still some value in this chain, right? Because AI can maybe help to define good properties of the objects, yeah? So if you have different pictures, you could say, I take the pixels as my columns in my table and feed that into the diffusion map. The problem is the radius in which you can do good comparisons becomes very small. And the diffusion map will still work eventually, but you need a lot of data, yeah? If your distance between data points needs to be very small, that you have a meaningful distance measure. Now, if you could feed your picture instead into artificial intelligence that extracts 500 properties, then that may give you a much better descriptor with which the radius in this new data space is bigger at which you can still compare, and that reduces your amount of data.
Mm-hmm. Anybody else? Okay.
If there's no acute question, maybe yes. I can voice again my weird hypothesis. So I talk mainly about physics approaches here and computer science approaches, right? And the title had ecology in it. So one thing you learn as an ecologist is to ask the right questions about complex systems. And your immediate instinct is to ask, why is it there? The second question is, how do we classify it? But why is it there? And if I think about culture and art, the immediate question that comes to your mind as an ecologist is, why do we have art? Yeah, why do humans do that? And you would think our ancestors, some spent their time producing art or looking at art, and some spend their time gathering food or having sex. And you wonder why this gene that makes us artists and admirers of art survived, right? Because normally you would say, hey, the people who had more food and more sex, they probably had more offspring, so they should have outcompeted us, yeah. But they haven't. So somewhere there must be the evolutionary benefit of art. And not everything that we have in our culture has a benefit. Not always for the host. Yeah, there's things like parasites. There's a famous example of the ant that climbs a blade of grass, and the ecologist asks why does the ant do that? What benefit does the ant get from climbing the blade of grass? And the answer is none. What will happen? It will happen by a sheep, but the benefit is to the parasites that's in the ant's brain and makes it climb the brain, this blade of grass, because this parasite needs to get into the sheep to reproduce. So maybe art is a little parasite that we have. I don't think so. So if we don't think so, then there should be an evolutionary benefit to making art and liking art.
So it's a little like saying it's an evolutionary benefit to science, right? So, I mean, this is a discussion which I think is we should be very careful. It's just like we should look at kinematics before we look at causation. We should look at all the possible theories that are out there or could be had in addition to the typical kind of evolutionary thinking. Because let me finish the sentence. So there is a kind of thing like humans do things which are not necessarily adding to their survival, right? Like I did a PhD in art history, which is not exactly like raising my...
Well, you get paid money for that.
And so the similar things you find in animals, right? Yes, bowerbirds do art, so to speak, to actually find a mate. But then there's many other animals that do similar things to just play. And so to say, right? So the question is, what is actually, so that's where I would actually make a strong case for data science, in a sense that you want to look at the stuff that is around before you come up with the hypothesis, which is sort of, if you look at like the recent papers on paintings, for example, that come out or have come out, there's a difference between people who have this kind of evolutionary psychology approach versus people who have a more data sciencey approach. We should sort of refrain from making these kind of assumptions. So I
disagree.
Yeah. Okay.
I disagree actually very strongly, because you're saying I'm not allowed to think this, right?
Yeah.
So I think one of my main points is all models are wrong, right? There's not the right theory.
Mm-hmm.
So thinking in these terms will not give us the ultimate understanding, but it's still useful. And you're right, your examples, yes, the bowerbird is very well studied, right? And the evolutionary game theory that leads the bowerbird to do all the things the bowerbirds do, from dancing to building little piles of blue trash, is very well understood. It has an evolutionary reason. So that is just an example of something where this exact sort of thinking allowed us to understand what's actually going on. And you say your PhD in art history doesn't give you an evolutionary advantage. No, but I would argue the mechanisms that are somewhere in your brain that cause some humans to study art history have given some earlier ancestors of you an evolutionary advantage. Otherwise, they wouldn't exist.
Mm-hmm.
Mm.
Yeah, that's good hypothesis.
So I like to make this point about art, because I think what I have this weird hypothesis, but I think it's a fun hypothesis to think about, that we like art because art makes us better pattern recognizers. So if you think about Disney movies, what have all Disney movies got in common, right? There's always good versus evil, yeah. And I think if you just grew up with Disney movies, you learn this good versus evil mindset, and that might be a good thing or might be a bad thing. But what you learn from that maybe is to classify people in good people and evil people. Yeah. Or if you look at a beautiful painting, maybe looking at this painting just teaches you to recognize a certain sense of proportions or a certain sense of place that you can then recognize in the real world. So, and this is somehow related to data analysis, because if you try to detect a cluster in some data and you have very few points, it's difficult, right? But if I could put some perfect examples of this data into this point, the cluster gets much easier to recognize. So, and perhaps that is what art does for us, that it gives us perfect scenes, perfect stories, yeah, that make it easier to cluster our life, so to make it easier to see patterns in our life, because art somehow provides us with perfect examples of a certain classification of a certain principle.
Yeah, any thoughts by anybody? I have thoughts, but I don't want to occupy the discussion. Yes.
Yes, just that's a thought-provoking thing as well, you know, in terms of art. I'd say also the opposite might also be the case, though. No, it could be the case that it brings, usually, at least the way art is taught and also talked about in arts and humanities discourse and so on, is usually the opposite. No, it has it has more to do with eliciting questions rather than providing ideal forms for recognition. No, so some of the kind of paramount works of art, rather, you know, films, whatever, are usually seen as the ones that do not conform to any form of previously known pattern and so on, which you could argue is also evolutionary in some way, no? And it's you know, it's maybe one of those, if you're, I'm not saying I am arguing it, you could argue, but you could argue it's one of these, the point at which some of these lines fork, no? For example, and then you get a new genre or a new whatever, no? But you know, even if we think about it in these terms, it would not necessarily you know, mean that or imply that it is either created or perceived as a pedagogical sort of endeavor, no? Not necessarily.
I mean, it is certainly not pedagogical on a conscious level. If it teaches us something, then it's probably on a subconscious level. But the first thing you said, that classically it's seen as eliciting questions, you know, that might just be the same thing, I would say, because again, this is maybe my physicist mindset, but if I understand something, then I can start to question, to break my model, you know? So if I understand good and evil, you can use these concepts now to formulate the question, well, can an evil person also be good? Can a good person also be evil? What makes a good person evil? What would make an evil person good? Yeah, now you get this next level of questions and you think about them. And then you recognize some themes there, and they give you then your next concepts.
Can I say something?
Yes.
No, like at the beginning, you were saying about being brave and put your model and simplify the system, no? But me as a practicing artist, I mean, the artists, when we're talking about art and the function and so on, the artists, they have to be also very brave and stand with their model. Actually, is one of the things, like art is one of the things much easy to be criticized and even amongst your colleagues. It's really like a knife wall, like there is a lot of knives, like cutting you in chop it in pieces. Means I think this idea of that you have to be brave and stand with your model is actually the same with the artist. You have an idea that you want, what you want to show, and you pursue, and if you don't do, then actually there is one model that actually is kind of working, that the only artists that they are very productive are successful. And someone wrote recently an article about there is no artist that we know, like that is kind of famous on history that did not produce quite a lot of pieces. Like there is no artist that had produced 2 pieces. And means this is actually validating what I'm saying. Like you have to be brave, because otherwise you like if you're not brave and produce like I'm sure that all they had a lot of criticism with what they do, like because you can I mean that's a normal thing that you know in life, that I mean everyone is saying, oh, I could do this, or yeah, these kind of things.
So what about the catcher in the rye?
The what? The what?
The catcher in the rye. It's one of the most famous books in the world, right?
Okay, yeah.
By an author who wrote nothing except this book, right?
Yeah, I mean, I was more talking about the artist. Maybe the literature is different. That there is a music also. Like there is one, like there is people who is known only for one song, and literature also for one book. But in the art,
there's actually a connection between you two. So there's a, Dashun Wang has done this science stuff where they looked at artists and scientists and I think also literature people. And the curious thing is, of course, like the problem is high impact is random, which is a big problem. So obviously, if you do only one work, you can have high impact, but for everyone that has impact, there's many, many people who don't make it. And then if you are what they call, if you have high Q, like if you have high quality, you can raise your probability for that random impact by just producing a lot. And so,
sorry.
Yes, go ahead.
So let me first propose I turn the screen share off now.
Yes.
We can probably see each other more properly. So good. So I would say, I mean, of course, that is true, right? More shots is the goal, right? But I would also say, I think it's right that it has to do with the genres. I think why you can do this in literature is you can work on one book and revise and revise and revise and make it better and better. Yeah, you can't do that necessarily on a painting if you're not working digital, right? So I think that your observation that most artists have to be very productive you need to practice a lot to get good.
I mean, the key premise is something we need to root in data, right? Like from Leonardo da Vinci, we have, I don't know how many paintings, 7 or 10. From Caravaggio, we have 89. So, the question is like always there, what did they do in the rest of their life? You can ask the same thing about Wittgenstein. He wrote 2 books and one of them actually appeared after his death, and the one that appeared during his lifetime was like that thick. And the second PhD advisor at Cambridge said like, I have no idea what you're talking about, but it's way over my head, and the way you impress Bertrand Russell, I give you a PhD, right? So the kind of key thing is, there is people who produce a very, very, very little and still are at that quality. But I think Mark, nevertheless, is right at the same time that you have to be brave as an artist, because, I mean, just imagine betting your life on like that one product, right? Like Wittgenstein gave up his wealth, and then he became an English teacher somewhere in the outskirts of Vienna because it didn't work out. And then he sort of like had his breakthrough, which is, so there's yes, I think there is this bravery thing is sort of something that's sort of interesting, but at the same time, there's many people who sort of fork that out. They say, oh, I have my life and I also do something else, right? Like I'm also a painter. I'm also writing something, but my life comes from something completely different. That's even true for people which we consider of like super important literature people, like Goethe, who earned his living with like sort of serving wine to his duke as the kind of, master of banquets. And so there's a lot of assumptions in this discussion we shouldn't have, because we don't know the frequency distribution of actually what's going on. And there may probably be a lot of heterogeneity, including heterogeneity in places where you don't think there are, right? Like one of America's foremost archaeologists was Thomas Jefferson, which you don't know for that, but he was. And so that's a really interesting kind of combination, right? And then obviously there's all this productivity in people that are marginalized, like people singing in the cotton fields, or women kilting because they're not allowed to, like, you know, do sculpture and get away with it, until women just took the right to get away with it, like Elizabeth Ney in the 1830s. And so there's a lot of interesting assumptions we should sort of like switch off. And that's where art historians often look at the data and before they model, because the key thing is there's so much phenomenon going on which actually defies the modeling assumptions which we have, and that's sort of the interesting thing. So what I would suggest would be interesting would be in this interplay between, say, ecology and art, for example. What strikes me all the time, my wife sort of is fascinated by nature and does a lot of kind of, you know, sort of not professional but naturalist work. And what always strikes me is that there's much more detail, there's much more interesting stuff going on in ecology. You can basically have the same variety as in all the art museums in Europe by just looking at a square meter of garden in your, you know, somewhere. And so that kind of thing is something interesting. And so what's the difference between Disney movies and actual life, for example, is, I think, an interesting question. What's the difference? Mila would give me right. What's the difference between pseudo-history and actual history and the sources we have? It's like, how can we bring this together? Why is it that people always want to have these simple ideas, for example?
Because simple ideas you can understand. But you have to simplify, right? Otherwise it's hopeless.
But just to say, many of these ideas are not necessarily that simple. No, there is also a lot of complexity that comes from this alleged simplicity. Also, if you think of Disney films in terms of plot, they do seem to be quite formulaic, no? And the good versus evil and this sort of thing. But there are many other instances in which they can be remarkably complex products in terms of, and to go back to your own point at the beginning, to model phenomena, no? And the phenomena is kind of a complex phenomena of production, consumption, which is not necessarily just encapsulated in the narrative of the film. You see what I mean? So there is, you know, this is still a lot of complexity to be unfolded, say, from even what appears to be a relatively simple or straightforward cultural product.
Yeah, I see you have a lot of knowledge of modeling, because like you nailed it with the redrawing the thing. Like I'm a practicing artist on digital, on art and technology, and there is just now few people that they live from very little works, because they are redrawing every time. There's a pieces of software that they actually are adapting normal installations, adapting in different ways, and they work for, I mean, somehow they became, you know, famous, but and then they adapt and they live from one piece rather than painters. They need to kind of practice and practice. And yeah, I take this as a very interesting, because you nail it on this thing. Really like.
I wanted to reply to Max also. I mean, this is a very, very interesting point, that how these social circumstances and methods of workings and influence the nature of output, right? Quantity and quality and measurable things, right? But I want to, it strikes me something that Max said is, I think we always have this discussion that the physicists just want to explore some weird histories, some weird theories, and the art historian wants to be careful and think very carefully. And this is a discussion I had so many times, very often with people from the social sciences, because they don't want to be wrong. Yeah, they don't want to think anything wrong. While in physics, we have exactly the artist approach. Yeah, to be right, eventually you need to make many different theories. Yeah. And why are physicists so happy to make wrong assumptions and try this model and try that model, formulate this theory and then a different one and then another one, is because in the end, a wrong theory in social science traditionally caused a major war in the community, while a wrong theory in physics just causes an experiment to be made, which settles it. Yeah.
Yeah.
So we have, and I think cultural analysis might be transitioning, right? Because of course you have more of a social science tradition, yeah, where you want to be very careful that you don't go wrong.
Mm-hmm.
But nowadays you have data, and data means you can de facto do experiments, right? If you have a hypothesis or if you have a theory, you ask, what hypothesis does this lead to? And once we have hypotheses that come out of our new theory, we can do an experiment. This experiment is just looking at the data if the hypothesis is true. Mm-hmm. So you can now dare to work more like a physicist does and less like a traditional social scientist does.
So I'd like to go back to Daniel. I think Daniel has a really good, interesting point there, which is that, you know, Disney and so on is complicated also, not or complex. So that basically feeds into the question, in some sense, you could summarize it into what is the nature of culture, or what's the nature of the Disney universe? What's the nature of Pokemon universe, in essence, right? Where, yes, social science is part of it, but then at some point you become a kind of zoologist of Pokemon monsters and stuff like that, which many kids are now. And so once you're at that row where you say, oh, I look at culture as a kind of natural phenomenon and I employ the entire method, and I can ask myself also, you know, like what Marge has said, artists have to work a lot, or very few can live of like a few. Like, let me give an example. And this, I think, is really interesting regarding this. There's a separation between humanists and physicists, but then at art production, at the highest level, which meaning the, you know, sort of the stuff that makes the most money, you actually have a confusion of computation, of art, draftsmen, and mathematicians. Like, let me give you this example. The DreamWorks, when they hired a CTO who was a physicist who worked for a risk, like a financial risk center, as like when he was a director of that. When he was hired by DreamWorks, what he did is he basically threw out all the draftsmen that would fill in the frame, like the kind of stupid drawing between the keyframes, and he hired 250 mathematicians. And the 250 mathematicians were tasked to actually fill in the frames between the master drawings of the keyframes. And there's a very interesting feedback loop. So the mathematicians still there, they have to continue to be there because they're sort of like calculating this ever better. If you have seen the DreamWorks movie become better and better with hair and atmosphere and water and like all sorts of stuff. And then the draftsmen, he said, like, you need draftsmen that are actually sort of Albrecht Dürer level, in essence, right? And it's obviously there's a tragic thing there, which is you have these super awesome draftsmen, and he says, like, they don't want people who know how to use Maya or know how to use some other computer drawing methods. They want people who are really good at drawing with pencil and paper. And then you have these super awesome mathematicians, but then there is no job for sort of mediocre mathematicians and mediocre artists and people who, like, even the very good artists, they have to go to YouTube and do their 5-minute pieces. But then the interesting thing is there's something like art analysis going on, and there's something like a physics of art going on, because these mathematicians analyze these frames, and the artists get feedback, typically very crappy plots of like some line splines, which have no meaning whatsoever, but they actually can, while drawing a face, see that the splines sort of do something, and they know, oh, if this has a particular sentiment and looks cool and witty, it takes, my spline bundle takes the following shape, so I can repeat it if I train it that way. So they become this kind of neural network in interplay with the mathematician. And that is sort of kind of, you know, it almost strikes me as this thing when the European Commission gets rid of the word research in the Commission of Youth, Technology and Education. This strikes me as like, this is the perfect application of that. You have like super talented mathematicians, super talented artists, and there's an immediate application. While what is not there is this kind of like, you know, the artist who thinks for 5 years, the physicist who does the model, why does this actually work? Where does this lead to? Or the artist who just sort of, you know, doesn't anneal to the spline, but actually tries to figure out what else can be done and stuff like that, which they basically brutally outsource and then just hire the best ones off YouTube in essence, right? So the key question is there something we in academia can do, much like in ecology, where we can actually, you know, treat this as a kind of societal phenomenon that we can analyze and actually sort of raise the issues with it, raise the dangers, but also raise the opportunities, because let's make no mistake, it would be great to have a kind of European DreamWorks, right? so the kind of key thing is like, in this kind of interplay, what is our role as academic cultural analysts, as physicists, mathematicians, artists, computer scientists? What would be the interplay and how does this look like? Similar to, you can ask yourself, what's the interior structure of the Broad Institute in Systems Biology? What should be the interior structure of a field like cultural analysis beyond the established kind of humanities, which is obviously not the answer how to react to what's going on in DreamWorks, I think. So how do you see the role of, like, you as a physicist, for example, in cultural analysis? What would be the, you know, other than being a co-author on papers, what could be achieved? What would be the insight?
What do you mean? I mean, for the insight from physics?
Yeah, so let me give you an example for the rest of the audience is the thing you did with forest patches. Maybe you want to talk a little bit about that? It's basically a mathematical modeling example where you basically save a lot of nature in Germany, in essence, right? So maybe you can explain it, and how do you get to that? Like, how do you find the example? How do you do this? How do you get the data? And how do you even come up with a project like this? Maybe
okay, so what Max is talking about is basically a little project we did where we ask, in nature, why is there actually heterogeneity? Why do different places look different, right? And of course, some of this is due to temperature also, but you also see that, like, if I look out my window here in Oldenburg, everything is flat, but then there's some places there's forest and there's some places there's not. So question is, can nature self-organize that? Can, starting from a homogeneous state, can it become heterogeneous? And what we did there is we thought, okay, this is our phenomenon. We look for dynamical instability where we start with a state where everything is the same. Can this be unstable to dynamics that makes it not the same anymore? And it turns out you can split the properties of the network of interactions that you put onto this physical space and the geometry of physical space and separate them. So basically, if I want to ask, okay, I have my system of 4 interacting species, there's trees, there's wolves, there's deer, right? And this system of 4 interacting species, when would this lead to spatial heterogeneity? I can work out a condition that then depends on the shape of my spatial system. So I can say, oh, if my system there is just a plane, then it wouldn't lead to heterogeneity within this plane. But if it has a hole, then suddenly it's possible. And these spatial requirements are a property of the 6 we put into space. So conceptually separating these two, that is where the interesting physics is, I would say.
So the question is, like, is it the fault of the presence of Gagosian Gallery and Serpentine Gallery that the art world is so unequal because everything is concentrated there? So would the addition of another fancy gallery in London in the same park that is functionally different, meaning not dependent on Hans-Ulrich Obrist and his friends, lead to an equalization across the art market? So that would be a similar question, right? And so that is, I think it's a space where modeling could be done, and probably is done, because let's make no mistake, there's hedge fund owners who think about art all the time. So the question is, how as a broader society can we sort of, you know, sort of have a more equal kind of notion of that. So that is, sort of, I think, a combination where physics and cultural analysis can go close together in essence. But the question is, I think the question is, and this is an important one, this discussion is a hard one because we need to raise the mutual understanding. Like obviously we already have this in this group, right? There's people who are artists, there's people who are humanists, there's people who are more theoretical, there's people who are more data or / sources driven, there's people who work with different genres like movies or the metadata about movies or texts and so on, linguistics. So there's a lot of discussion we need to have, like how about the naming game of like what we're actually talking about, what we're actually doing. And the question, I think one of the hardest questions is, so how do these kind of cross-domain multidisciplinarity, where you have the physical sciences and the social sciences and humanities, like how do we actually get together? This is like one of the hardest questions we could actually solve, right? And it would be, this is the reason I invited you, and I think this is something we should work on in essence.
Yeah, but for me, this is not really such a big problem almost. Mm-hmm. I mean, I think that, so if you mention this example of galleries and fame, I mean, that is what Darshan 1 does basically, right?
Yes.
And as a physicist, you know, now I fall for the physicist folly and be totally overconfident in my ability to model that. But you could say, you know, population is distributed across a planet. A gallery can survive if it attracts enough people, right? Obviously, the more people you attract, the more famous you're going to be. The better the works you have, the bigger the radius that you attract people from. And what changes is the mobility of people. So do you fly to New York to go to a museum? Maybe today. Yeah. And of course, if you look back to the 10th century, right? You wouldn't have done that because there was no flight to New York, right? So of course you could say maybe the 10th century kind of had more equitable art, right? Because there was more places where you can get a special number of people to look at your art. Well, total number of people has been lower, right? People have different things to do, but there's things like there's a formula there, right? How much people could your museum in London attract?
Yeah, I think it's hard to discuss, right? Because like, again, the question is what the function of a gallery actually is. Is it attracting people? Gagosian is not like the MoMA where there's 20,000 people every day, for example. Yeah, so we ran out of time actually. We have 2 hours, so we have time, we have 3 minutes left. So who has a last question? Nobody? Okay.
Maybe can I come back to Daniel's point of the complexity in the Disney movies? I think that's the beauty. And I think in physics, what everybody loves is you have a very, very simple system that still produces very complex dynamics. Yeah. So where things get rich, but based on simple premises. And I think in art, I see sometimes similar things. Yeah. I think for me, at least some of the pieces of art I like both are very, very simple elements that still cause a complex impression. Yeah? And if you think of what can we do for the Disney movies, right? I somehow think in the future I would love to say Diffusion Map actual movies. So that's, of course, that's a bit ambitious, right? I can stuff all the pixels in a picture, maybe in a diffusion map, but I can stuff every frame in a movie, and it seems so overly ambitious. But maybe we can find a good representation of plot, yeah, and kind of do the diffusion maps of plot, and then you would say that there is something like the Platonic ideal of the Disney plot, yeah. So the center of this cluster of plots, or that is there's the edges, or the least Disney movie, or I don't know.
Can I say also that I mean, I think you're right about the I like this idea of emerging dynamics, no? which is, I think, something that sometimes is not from the cultural side is not often considered as a you know, and these dynamics can emerge from relatively simple interactions, but it's also maybe the focus on the interactions, not just the objects, as in say, you know, because the objects as, you know, films with pixels, but also the interactions that people have with these objects are incredibly rich. So I think the really cool thing about the census is that it kind of captures a snapshot of that, no? Whereas maybe what we're lacking in terms of the culture world is also some form of census-like standardized snapshot that cuts across and lets us see the interactions as well as the objects, which I think sometimes that's a complicated thing about culture, or where culture gets really messy in many. Sometimes I think what I'm trying to say is sometimes a lot before the mathematical modeling even happens, there is already a lot of mess to deal with in terms of where we get this information and, you know, how. And I think
I won't even start telling you about the mess we face in ecology.
okay. But we could share messes at some point.
Yeah, but I think this mess is just the preliminary work kind of characterizing and throwing out details or so. And I mean, if one thinks about the movies, right, the first thing is we can take the snapshot, right? We can characterize the plot somehow. I mean, this work that's maybe not done, but maybe we can bring it into a kind of a standard format where we can then mathematically compare plots.
I mean, we will try, probably.
Nice. Anybody else? Okay. So then with that, I would like to add one last sentence, which is the best known food web, according to Jennifer Dunn until very recently, was the predator-prey network of the Cambrian explosion, which is definitely a historical food web network. So maybe in art and cultural history, we are not so badly positioned with having good or bad data, because a lot of work has gone into it. And so this may actually be a premise for the future to look at that more closely, because much like ecology, contemporary culture has this issue that there is so many opportunities. Well, as you go back, your data becomes less and less. And, you know, something like the body of 19th century newspapers may be something that's actually something you can carry around on a laptop in a couple of years. And so there may be actually something that can be done in that realm. So with that, thank you very much. We hope to stay in contact. For everybody who is not part of the CUDAN group, thank you very much for being part of this discussion. And we try to repeat this every week. As always, this will be subject to availability. So some weeks we may have two, while one week we may have nobody. Next week is, until now, still open. In 2 weeks, there will be Simon Dedeo of Carnegie Mellon University, who is an astrophysicist, but is a professor for humanities and social sciences. And he started a cultural analytics program that is it's an NSF-funded institute, or NEH-funded institute, so a postdoc kind of summer school for that. So that's our next kind of glimpse into how do other people do cultural analytics. Thank you very much.
Let me maybe say thank you very much for the invitation. It's always great to have an opportunity to think about these things.
Yes.
And invitation to everybody. If you think math or modeling or so makes your life easier or could make your life easier, get in touch. Goodbye.
I totally will. Bye-bye.